Okay, sir. Hello, hi everyone. This is V. Deepika ma'am, working as an assistant professor from KG Reddy College of Engineering. Now let us discuss today about the transistor biasing and stabilization. Before discussing about the transistor biasing and stabilization, let us discuss about the operating point. Okay. Now already I think so you are familiar in the first topics that transistor have been having three regions. Okay. Active region, cutoff region, saturation region. Let us discuss about the three regions and we will discuss about this operating point. Okay. Now we are having three regions. Okay. Active region, cutoff region and saturation region. These three regions are there based. This is nothing but the region of operation. Okay. Coming to the region of operation, okay, when the emitter base junction, okay, we are having two types of junctions, okay, in your transistor, emitter base junction and the collector base junction. Okay, the transistor would be working in these three regions. So, when the emitter base junction is forward biased and the collector base junction is reverse biased, then the transistor is been working in the active region. And if the cutoff it means when the emitter base junction is reverse biased and collector base junction is reverse biased, then transistor is working in reverse active cutoff region. When the emitter base junction is forward biased and collector base junction is forward biased, both the junctions are forward biased, then that point is nothing but then the transistor is working in saturation region. Now these three regions, for these three regions we are applying some external DC voltages. So to get these three regions. Now let us discuss about the why it is necessary for this biasing. Okay, we are now applying the external DC voltages. Is it right? So that application of that external DC voltages is nothing but called DC biasing. Okay, but we are having some question that why it is necessary for going for biasing. Okay, now in order to operate the transistor, okay, once a minute, let us discuss about this need for biasing. Just okay. Now we are having that question that why it is necessary for the biasing. I said in order to operate the transistor in the particular region, if I want to operate the transistor in active region, okay, we need to apply some external DC voltage of correct polarity and the magnitude of the two functions. So that is the first point, and the next point is nothing but for the transistor we are having some we know that amplification. Amplification is nothing but what? The output signal power will be greater than the input signal power. How come we are getting the output signal power to the when we are output signal power greater than the input signal power? We are having this kind of question. So when we are applying the external DC voltages of the correct polarity and magnitude, we can achieve the output signal power greater than the input signal power. So these are the two important criteria conditions why it is necessary for biasing. So to operate the transistor in particular region, and to get the output signal power greater than the okay. Now, let us discuss about the another topic in this one, Q point and stability factor. Okay. Now, what is meant by Q point? Okay. Now, Q point is nothing but, as we are applying some external voltages. So, this external voltages would be generating some voltage and current. That voltage and current are nothing but that point DC operating conditions. Okay, the intersection of your AC load, when you are plotting the AC characteristics and DC characteristics for a particular transistor, where the intersection point of this AC characteristics and DC characteristics is nothing but your quiescent point or DC operating point. Okay. Now, but this now had said that to operate the transistor in a particular region, we are applying some external DC voltages. Okay. But that point would be shifted due to some factors like the transistor parameters such as IC0, beta and VBE. Okay. So, due to these three transistor parameters, the region of operation of the transistor, means the operating point or the quiescent point would be changed. Okay. So, in order to make the transistor, we need to make the transistor in the particular region, we are it is necessary for applying some external DC voltages. But what I am saying that due to this IB factor, beta factor and IC0 and VBE, the operating point would be shifted. As well as these three transistor parameters are temperature dependent. Okay, with the variation of the temperature also, the operating point would be shifted. Okay. So, the stability factor indicates the degree of change with respect to the change in the temperature and IC0 and IC0, beta and VBE. Okay. Now, let us discuss about one simple bias configuration, which is nothing but fixed bias configuration. Okay. Now, I am drawing some simple circuit. I am applying AC input signal. Base resistor. I am applying this one. This one is base, collector and emitter, and this had been grounded. Some voltage would be generated between the base terminal and the collector emitter terminal, and some VCE voltage would also be generated between the collector terminal and emitter terminal. So, this is some simple fixed bias configuration circuit. Now, once a minute. So, this is some simple fixed bias configuration where we are using one input capacitor for coupling of the input power to your base of the transistor, and one transistor RB has been placed, and one RC load resistor would be used, and where these resistors would be given to the VCC supply of 12 volts or 6 volts of the requirement according to our requirement, and the emitter terminal has been grounded, and we are keeping one more capacitor here, and we are taking AC output signal at this point. Okay. Now, this is one of the simplest fixed bias configuration. We can draw even simplest DC equivalent for this configuration by simply making the capacitor open. Okay. That by making the capacitor open, so we will get the reactance. Why? Because the reactance of the is given as infinity. Actually, the capacitance Xc equals to 1 by 2 pi Fc. Here we will get as infinity by applying 0. So, as the reactance of the capacitance is infinity, we can replace the capacitors by an open circuit. So, now let us draw some DC equivalent configuration for this fixed bias configuration. Okay. When I just draw the DC equivalent, I would be getting only with resistors and voltages. Okay. This is simplest DC equivalent for the fixed DC equivalent circuit for fixed bias configuration. Okay. Now, let us discuss about the base circuit in this DC equivalent circuit. Okay. Coming to the base equivalent circuit, okay, how can we draw? Just take only requirement of base only. Emitter would be grounded as usual, VBE, base, emitter, and this one. I am just taking the base circuit. Okay. Now, apply KVL to this base one, then we will get VCC, minus IB, RB minus VB equals to 0. Then I can write VCC equals to IB, RB plus VBE. But I want the base current. Okay, I want base current. So, shifting this to base 1 and making the resistor RB to be on your denominator on your left hand side, we would be getting the base current as VCC minus VBE by RB. So, this is your base circuit. Now, let us draw for your collector circuit. Okay. Now, draw for your collector circuit. RC will be there. Okay. IC current, VCE, these. This one is collector terminal and emitter terminal. Now, we are discussing about your collector circuit. Now, by applying the KVL to your collector circuit, then what you would be getting? This one is VCC, no? VCC minus ICRC minus VC equals to 0. Okay. Now, I will be getting IC as what, ma? IC equals to VCC minus VCE by RC. Okay. But we know that magnitude of the collector current can be written as IC equals to beta IB. Okay. Means what? The collector current, the output collector current is depending on your IB current. Okay. Base current, this base current is dependent on your RB base resistor. Okay, nama? So, change in the output color, but it is not depending upon your RC. So, it is as the base current IC equals to beta IB. So, the collector current is dependent on your base current, but it is independent on your RC. Okay. So, that if you are changing any RB resistor, then there will be a change in the collector current. But if there is a change in the RC, if there are any changes in the RC, it will not reflect in your IC. If there is any change in your RC, then it will be reflected only in your VCE. Okay. Now, we can even write that VCE equals to VC minus VE, and VBE can also be written as VB minus VE, but here VE is nothing but 0. So, we can directly write VC equals to VC and VBE equals to VE as VE equals to 0. So, this is the simplest fixed bias configuration. So, this is if you are having any doubts, you can say. So, this is my end of the session. Let us continue in the next bias configuration in the next session. Thank you.